Hello, I'll be presenting the GPS programming language on behalf of Team 10 for the SER502 project. So, the agenda for this PPT is GPS programming language features. Then we'll have a discussion on design of the compiler, then a design of the runtime environment, followed by a demo of a few programs. So, talking about the GPS components, we are using Antler 4 for scanning, parsing, and intermediate code generation. The Java runtime environment is used for GPS runtime as well. So now going forward with how GPS works. So we have a GPS .gps file extension which indicates that the source code is in the file for the GPS programming language. So this .gps file is input to the parser to generate a bytecode file with an extension of .gpsb. So this .gpsb indicates as GPS bytecode. The .gpsb file is then input to the runtime environment to produce an executable. Uh, uh, Talking about the supported data types and operations, we are supporting three data types, which is int, boolean, and stack. Uh, there is an assignment operator, some conditional statements, and mathematical operators. All follow the syntax which is of the C programming language. Moving forward with the supported operations, we have the decision constructs and iterative constructs, which are if statement and while statement, respectively. The functions in this programming language is inspired by the Swift syntax. One particular point to be noted about the functions is that it has a declarative part in its block, which makes sure that all the variables are declared at one place to avoid any compile time errors. To avoid any runtime errors, I'm sorry. So going forward with functions, so this is the same as I explained in the last slide. Talking more about blocks, we have dynamic scoping, which is permitted due to nested blocks in this programming language. And there is an inner block which can access variables of surrounding outer blocks, which is essentially the dynamic scoping. Okay, so I'll talk about Antler now. Antler is an abbreviation for another tool for language recognition. It provides a framework to construct recognizes parsers, interpreters from a given grammar input. The grammar format of the used in the Antler is inspired by EBNF format, which with a slight modified syntax. Now, uh, the Antler is composed of three parts, which is a lexer, parser, and a parse tree. Uh, the lexer it reads a character stream, which is basically a source code to be compiled, and outputs a token stream. This token stream is then used by the handler to generate a parser, and this parser is used to generate a parse tree. So now I will demonstrate how Antler works to generate a parse tree. Okay, so this is the source code which we'll be using to generate a parse tree. The main point here is to highlight this expression to see how the precedence of the operator works through the grammar. So if I run this, we'll get parse tree. Okay, here it is. So if you see here, this is n equal to a into b minus c. So so as we traverse the tree, we will have multiplication of ab first, and then subtraction of c from the product of a and b, which is then assigned to n. And the rest of the code is just declaration statements. So this was about Antler. Now, when we have to traverse the parse tree, we generally use a visitor or the listeners. The visitor approach is much more flexible than the listener, which we have adopted in our programming language to parse a parse tree. The parse tree generally has each node which represents a grammar rule based on the input token, and the terminal nodes are the values which are generally on the right hand side of the grammar rules. So on this slide, you can see the overall view of the Antler. Here is the tree walker, parser, lecture, and output. So now I will hand over to my teammate to.
Further, we'll look through the design of the runtime environment. The virtual machine has three fundamental components: the activation frame stack, instruction pointer, and the bytecode. The bytecode stores full intermediate code generated, and the hash map of function definitions. This function definition not only includes the code but also its return type and parameter information. This information will be useful in error checking when the function is called. Let's go on to the activation frame stack. Activation frame stack maintains the activation records as and when the functions are called, has information on the return value, return address, name of the function, and the two stacks, which are block stack and operand stack. The block stack is introduced for scope handling, and operand stack is to store intermediate results. When we say block, we refer to functions, if else constructs, and loops. Let's go on to the demo section. In the first program, we will demo the if else nesting and the if else control statement. In this, we are we run a program of finding three maximum integers. We passed value 4, 3, and 5. X goes on those four values assigned to x, 3 to y, and 5 to z, and we expect that the output would come out as 5. So we see that the output has come out as 5. Next, go on to the next program. The next program is of mathematical operations and nesting of while and if loops. So here we are calculating a sum of first 20 odd numbers. So as we know, with arithmetic progression, we expect that the output should come out as 100. So we see that the with intermediate results, we see that the output has come out to be 100. We go on to the next program, which is demonstration of stack and its fundamental operations: push, pop, and peek. So in a stack, we push values 1 and 2, and when we pop, it would come out to in the reverse order. So we expect 2 and 1 to be the output. So here we see that the output has come out as 2 and 1. We go on to the next program. Next program is showing up dynamic scoping. We have a variable declared outside this if block, and the same variable is declared inside too. So in the initial first print statement, it will use the value of the outer block, and once the variable is again declared, it will use a new value. So first we expect, so the output here we expect as 1, 6, and 1. So the outer block will again use the last print statement will use the value of the outer block. Okay, the further we see the demonstration of a factorial function in recursion form. So here recursion uh, is demonstration of how multiple frame stacks, multiple f- frame information is stacked over each other. So we are calling function over and over again to calculate a factorial of 5. We expect that the output would come out to be as 120. Okay. Further, we'll move on to the next program, which is calculating factorial in another form, which is iterative. So here, iterative is performed with the help of while loop. We are looping over and over again until the value is turned out to be 1, and multiplying those numbers. So again, since the value is passed as 5, we expect that the answer should come out to be as 120. Okay, so this, as we conclude to the section, to our presentation, we like to highlight on what requirements we have met. So if we have met the initial requirements of intermediate and generating an intermediate code, supporting primitive data types, integers and booleans, a data structure which is stack, control statement if else, a loop, recursion, dynamic scoping, mathematical, logical, and assignment operations, along with error handling, which has happened at both compiled and runtime. So this concludes our presentation. Thank you.